We're back. This is a continuation of our introduction to electric charge and electric force. We're going to work now a problem involving a calculation of the force on a test charge. Here's the situation. We have a 4 coulomb positive charge there. 6 meters away, there's a negative charge, negative 3 coulombs. Along the line joining the two charges is what we can call a test charge, a charge which we'll label as Q naught, and let's suppose that charge is a positive charge. We want to determine how far from the 3 coulomb charge may we place this test charge of any value whatsoever and have it remain there when we release it. In other words, how far, call it x, from the 3 coulomb negative charge may we place any positive charge such that it doesn't accelerate? In other words, such that the net force, total force on it, is 0. Well, there are two forces that will be acting on that test charge. There will be the pull to the left by the attracting negative charge, and a push by this positive charge on this positive charge, a push to the right. I show those two forces here. The force labeled B is the pull by the negative 3 coulomb charge, a pull to the left on this positive charge. Now, attempting to counteract that pull by the negative 3 charge, we have a push to the right by the positive 4 coulomb charge acting on the positive test charge. We label that charge A. Those two charges, those two forces must be equal in magnitude, so that a pull to the right, or you can call it a push to the right, is counteracted by a pull to the left, so that the forces are in balance. So the force A must match the force B. A and B, keep in mind, are the magnitudes of the forces, absolute values of the forces, the positive numbers. And so we set A equal to B. Force A is the push on the positive test charge by the 4 coulomb charge. So the force law is KQQ over R squared, KQQ over distance squared. There's your K, there's your Q, here's your other Q naught. And then the denominator squared is a distance squared between this charge and that charge. The total distance between this charge and that charge is 6, plus whatever x is, our unknown distance x. 6 plus x, then square it. Now let's look at the right side of this equation. The force B is the pull to the left by the negative charge pulling on the positive charge. So it's KQQ over distance squared, same pattern as before. The force between two charges is KQQ over distance squared. Here's your K, here's your Q. Don't forget we're using absolute values of the charges that appear in our KQQ equations. So it's K times positive 3 times Q naught, KQQ over distance squared. In this case, the distance is from here to there, a distance x, it gets squared. Now we can simplify this equation before we try to solve it by dividing both sides of the equation by KQ naught. KQ naught appears in the numerator on both sides. Divide the equation by KQ naught, and the KQ naughts cancel. And now we have a simpler looking equation. 4 over the parentheses squared equals 3 over x squared. But what I'll do is reciprocate both sides of this equation. In other words, turn both sides upside down. So now we've got the parentheses squared over 4 equals x squared over 3, which I'll further simplify by removing the fractional nature of this equation. We don't like fractions in our equations, do we? I'll multiply both sides of this equation by 12. And so that puts a 3 on that side and a 4 there. There's your Well, that's not what I'm going to do actually, now that I think about it. I'll just multiply both sides of this equation by 4. The 4 disappears there, and it's multiplying there, and there is the equation we have. Now, what I'll do next is take the square root of both sides of this equation, remove the squaring sign there to give me 6 plus x all by itself. And 4/3 square rooted is 1.155, and the square root of x squared is, of course, x. Bring this x over to the right side. That subtracts an x from what we already have, leaving just 0.155x over here. 6 is on the left side. Now reverse the order left and right, as I did here, and divide both sides of the equation by 0.155. Final answer, 38.7 meters. Now, maybe you don't like doing the problem this way. You're not that good at solving equations longhand or by hand, as we say, and you come to rely on the solver feature of your calculator to do your equation solving for you. That's fine. That's what I usually do. Be aware, however, that every quadratic equation, that is to say any equation that involves x to the power of 2, has 2 solutions. Now, if you're lucky, when you use your solver to solve for the value of x, you'll land on the right answer right away. You'll know you've landed on the right answer if you obtain a value of x that is positive. The other answer would be negative. If you're unlucky, you might land on a negative value of x. You must reject it. Here's what the other solution is that you have to reject. There's the one that you'll get using your solver. The other is a negative number. Depending upon what your last seed was, your last choice that you used on your solver, you might end up with a negative value of x. Bad luck, but just reject it and pick a different seed so that you land on a positive value of x. We know x has to be positive because this distance from there to there is some positive number. So this is what you would get, the 2 different solutions. One is positive, that's the good one. The other is negative, that's the bad. Reject it. Final answer that is this. You may place any test charge you want that's positive as a distance of 38.7 meters from that charge, and that charge, Q naught, that you place there would experience 0 net force. It would remain motionless. Well, I hope that was understandable to you. I'll perhaps work some more problems involving electric forces in the next lecture.